Hi kids, today we're talking about the Doppler effect. The Doppler effect is a change in waves produced by a moving object. You'll see in this little simulation from McGraw-Hill that there's a sun that's giving off waves. Maybe those are light or X-rays or gamma rays, one of our parts of the electromagnetic spectrum in any event. And we're sitting on the spaceship, and you can see, if you watch the cursor there, the waves that we are viewing from that sun or that star. You notice the waves are nice and even, because the object producing the waves isn't moving at all. But if that object starts moving, it's going to change how the waves appear. Not that it's making different waves, but that it's going to affect how the waves are. So I'm going to start this sun moving and we'll be able to observe what's going on. You'll notice now that as the sun is producing waves, it's catching up to itself. And the waves produced from the front of that sun are closer together than they were before. If this is light, that means that those waves with a shorter wavelength and a greater frequency are going to appear more blue. The ones behind are farther apart. They have a greater wavelength and are less frequent. So they're going to appear more red if we're talking about visible light again. That redward change is called a redshift, and it's one of our big indicators that we have that the universe is expanding. If we look at the stars that are out there and we compare the frequencies of light being given off from those stars to what we expect from hydrogen and helium, then we'll find that the frequencies are a little more red than they should be. Some of our big proof that the universe is expanding. But the Doppler effect can happen with anything producing waves. It can happen with sound too. You've probably observed it before. This is a video of a train. Let's listen and hear. That change in pitch you heard was due to the Doppler effect. The train coming towards us was producing a higher frequency to us, the observer on the side, than people on the train would have been hearing. As it passed, we heard the shift to a lower frequency, a lower pitch. That's because those sound waves were more stretched out on a greater wavelength and lower frequency. So we've seen the Doppler effect with light and with sound. Now, how do we use it, other than just listening to trains go by? Well, here's one of the most important ways we use it. That's with our weather predictions. This is a Doppler radar map. This one's from northern Indiana. And if you look, there's a little arrow that says tornado circulation. Never a good thing to see on your radar map, especially if you happen to live close to that spot. The green indicates places where the wind is moving towards the Doppler radar. The radar has sent out radio waves and microwaves. Those waves have bounced off of the air formation there and have come back compressed, meaning that that air formation, whether it's a cloud or just a large air mass, is moving towards the radar source. If you notice where it's red right here, that's where the waves have been stretched out. They've bounced off of something that's moving away from the radar. So we've got one spot that's moving both towards and away from the radar. And that's got to be spinning. It's the only time we can get something moving towards and away from you at the same time. And that spinning right there is an indicator of rotation, possibly a tornado, and it would take people on the ground to tell whether or not that it actually touched ground or whether it's moving. Now this one happened to be from 2002 and was observed over Van Wert, Ohio. So those folks there hopefully were ducking and covering. That's the Doppler effect. Waves from a moving object are shifted, and they're compressed as that object moves forward, and they're stretched out as that object moves backwards.